Depending on who you ask in the scientific community, baryonic matter makes up 5 to 20% of our universe, the rest being taken up by dark matter, whose gravity bends the universe to its will and slows the constant expansion of the universe down, and dark energy, which counteracts this, speeding the expansion of the universe up. But 29 new scientific papers are painting the largest and most accurate map of our universe and its evolution since the Big Bang. We're going to talk about this paper, as well as the fact that there are hints in this new survey that predict a universe that is at least 5% smoother than we originally thought. But first, be sure to hit that like button, smash that subscribe button, and ring that bell to never miss a video. I'm Eric Malachite, author of Mind's Horizon, and this is ScienceGad. These 29 papers utilize the 570 megapixel dark energy survey camera, or DECam, at the Site Clean Room to image the night sky. DECam was designed and built at the Department of Energy's FNAL, specifically for the DES, and it just so happens to be one of the most powerful cameras in the world. From 2013 to 2019, the DES used 30% of the time on the Blanco telescope to survey a deep field, or 1/8 of the night sky. Hundreds of millions of objects were cataloged over the course of 758 nights. And of course, the DES just came out and announced the results, the largest and most comprehensive map of our universe, mapping the distribution of galaxies at relatively recent epochs. Steve Heathcote, CTIO Associate Director, had this to say about the new DES survey. NOIRLab is a proud host for and member of the DES collaboration. Both during and after the survey, the dark energy camera has been a popular choice for community and Chilean astronomers. Baryonic, or in other words, normal and visible matter, makes up a small percentage of our universe. Dark matter and dark energy make up the rest. The universe isn't evenly distributed, but forms a cosmic scale structure composed of smaller filamentary structures called the cosmic web, which we recently did a video on that is linked in the description. And one phenomena the DES specifically used to identify dark matter was gravitational lensing. The DES studied nearby galaxies as well as those in the deep field we mentioned earlier. For a breakdown on what a deep field is, check out our video on the Hubble Ultra Deep Field, link in the description. And its new maps give us a glimpse into the large-scale structure of the universe, as well as a picture of how the cosmic web evolved over the last 7 billion years. DES relied on the observations of two phenomena to calculate the distribution of dark matter as well as the effects of dark energy. The first is the fact that galaxies aren't distributed randomly throughout space, but form the web-like structure that we just mentioned. But what we didn't explain is that this structure is caused by the gravitational effect of dark matter. The second phenomena DES looked for were weak gravitational lensing effects, which are phenomena caused by the light of distant galaxies being bent by objects, like other galaxies, that are in the way of its path to reaching us here on Earth. Dark matter can bend this light's path as seen in these images. Gravitational lensing only happens with objects with massive amounts of matter. For example, smaller objects like our sun produce gravitational lensing effects as well. And we're planning to launch a telescope that will take advantage of this effect to produce higher resolution images of distant objects called the James Webb Telescope, which was recently delayed. Again, man, we should really do a video on the James Webb Telescope, shouldn't we? After all, we've mentioned it like a million times. But these events are also thought to be a possible signature of dark matter. The DES used this as a means to study how the apparent shapes of distant galaxies are positioned in relation to each other. Through line-of-sight observations, the scientists were able to infer the clumpiness of dark matter in the universe. But what does that even mean? The new dark energy survey has generated the most accurate picture of the universe that we've ever seen. But there are hints in earlier DES data that the universe might be at least 5% less clumpy than originally predicted. So what does that mean exactly? Well, in the standard cosmological model and in the cold dark matter model, dark matter can form smaller clumps. In these Hubble Space Telescope images, we can see 4 distorted images of a background quasar and its host galaxy surrounding its core of a foreground galaxy. By observing the gravitational effects in this system, researchers were able to indirectly measure dark matter, finding them in cold dark clumps. We've been able to indirectly detect clumps of cold dark matter before, which is kind of news to me. But these images show far smaller clumps than ever measured before. These observations conform to the cold dark matter model as well as the standard model. But what about the results from these 29 papers? Well, according to one paper's abstract, only a small part of the data vector shows less clumpy parts of our universe, but that discrepancy from the team's expectations set by the standard model equaled roughly 1.5 to 5%, which is still very unusual. However, it would be easy to mistakenly think that this less clumpy universe is somehow in violation of the standard cosmological model, but this isn't quite true. DES scientists compared their results to measurements from the ESA's orbiting Planck observatory. Planck uses the cosmic microwave background, or CMB, to peer back into the early universe as well, roughly 400,000 years after the Big Bang, which, if you've been a longtime watcher of the channel, you know that that's the same amount of time the latest version of the Hubble Ultra Deep Field is able to peer back to. This data paints us an accurate picture of the universe 13 billion years back, and the standard model predicts how dark matter should have evolved throughout the evolution of our universe. Now, the combined conclusion of these 29 papers seems to be that the current standard cosmological model of the universe has been vindicated, despite this potential 5% discrepancy. To figure out why they concluded this, we have to go back to the deep fields that the dark energy camera imaged. Redshift information from the deep fields was used to calibrate the rest of the survey, and when these images were stacked together, it allowed astronomers to peer at more distant galaxies, allowing these scientists to pinpoint the density and overall clumpiness of the dark matter in these areas. In fact, this is thought to be the most accurate measurement of dark matter to date. For now, the mystery of a less clumpy universe than predicted is just that, a mystery. But don't think that the story is over. This DES survey was completed in 2019, but the job is actually only halfway done. The team has only surveyed half of the dataset, and the last half of the data is expected to show us an even more accurate picture of the dark matter and dark energy in our universe. DES director and spokesperson Rich Cron, a Fermilab and University of Chicago scientist, said in relation to the work, "The collaboration is remarkably young. It's tilted strongly in the direction of postdocs and graduate students who are doing a huge amount of this work. That's really gratifying. A new generation of cosmologists are being trained using the dark energy survey." Chris Davis, NSF's program director for NOIRLab, concludes by saying, "DES shows that the era of big survey data has well and truly begun. DES on NSF's Blanco telescope has set the scene for the remarkable discoveries to come, with Rubin Observatory over the coming decade." So, to summarize, the consensus of the DES, which consists of over 400 scientists from 25 different institutions in 7 countries, does not think that this hint of a discrepancy is a major blow to the standard model, but with only half of the data set surveyed, this could potentially change. What would it mean if the universe was significantly less clumpy than even this survey predicts? And how would we begin to explain that? I'll leave that for you to speculate in the comments. If you dug this content, be sure to drop me a like and do the thing I just suggested. And yes, I'm sorry I sound terrible. I am getting over a summer cold. Should be back to normal in the next video. And be sure to smash that subscribe button, ring that bell to never miss an episode of the show, and check out the Patreon while you're at it. Couldn't hurt, right? And speaking of which, look at all those names. Thank you, patrons. I'm Eric Malachite, and I'll see you next time.